Hi. So, having looked at all the details of backprop for modules such as fully connected, ReLU, and cross entropy, having written all of it by hand, creating our own PyTorch like framework, and so on, let's move on to something which we do on a more daily basis. So we don't usually code it up from scratch unless and otherwise you're writing maybe like a new layer, a new module. But we had to do it so that we are confident about ourselves, so that we know what is happening under the hood. But now that we are done with the difficult things, let us move on to the more interesting things. And one of the interesting things is transfer learning. So in real life, what we do is we transfer the learning of some other bigger model that is already trained to achieve our goal. Right? So that is why this word transfer, because we transfer the learning of something that is already done. So in some sense, we stand on the shoulder of the giants. So and especially because this week we will start to kind of do our first project, we need to know, and this is kind of a myth, that neural network need a lot of data to train. Well, neural networks do need a lot of data, but it is in some sense also a myth. Why? Because you do not usually start training neural networks from scratch, especially the modern neural networks, the LLMs, the diffusion models, the feature extractors. So you may have heard of LLMs such as OpenAI's LLM. These are proprietary, where we do not have access to the model. But there are then LLMs which we have access to, such as the Qwen 3.8b, or let's say the Kimi K2, etc. And we'll talk more about them in the next weeks. So these are LLM. Then there are feature extractors. Such, for images, you have Dino V3, for example. Right? So all these are networks which have been trained on massive amounts of data, which we call the internet scale of data, right? And it takes millions of dollars to actually train these. But once they are trained, we have access to them. And that is usually our starting point. So we will always either resort to fine tuning, and sometimes we won't even do fine tuning. For example, in the case of a RAG, a retrieval augmented generation, which we'll talk about today in this video. So for example, ImageNet used to be a large data set, right? There was this ImageNet competition. We'll talk about ImageNet when we talk a little bit about history of machine learning and neural networks. But ImageNet has about 1 million images in the training set, and it has 1,000 classes, right? So 1,000 classes, and it has 1 million training images. Now, usually when you want to maybe fine tune a network on, say, your image data, so you have a bunch of images and you want to do something on it. Let's say you want to do classification, right? What you would do is you would already train this giant. So you would start with a giant network that is already trained on ImageNet, and then you would use it on your data to fine tune it. Right? So then you would have maybe your data, which is much smaller than the ImageNet data, and you would then fine tune this model that is already trained on, say, ImageNet. And ImageNet dataset is just an example, right? We have internet scale datasets these days. So how would this transfer learning work with the ImageNet dataset? Let's go on to like a really simple network that Alex Krzyzewski created, right? So Alex and Hinton from University of Toronto, they came up with this they came up with this AlexNet, right? And this AlexNet looks a little bit like this. So this is AlexNet. And AlexNet, you start with an image of some resolution. There are so-called convolutional layers, there's so-called a max pool layer, a bunch of these put together, and then what happens in the end is, after the last max pool, you flatten. So after convolution, usually you get a volume. We'll learn about all this. You don't worry about the details, but usually what happens is, like you get maybe something which is spatial. So you get like a volume. It could be of dimension say 32 into let's say 16 cross 16. So usually we say okay, it has 32 channels, right? So the depth is the channels, and then this 16 cross 16 is the height and width. Yeah. So but don't worry about it. What I want you to know is after this what you do is you do this flattening. So you do 32 into 16 into 16, so 32 is 2 to the power 5 into 2 to the power 4 into 2 to the power 4, right? So you have 32 to 5 and 4 and 4, so you have like a giant vector of size 2 to the power 5 into 2 to the power 9, right? 2 to the power 8. Yeah, and so you have flattened it. So you have flattened this cube into this one giant vector, and in this giant vector then you have a fully connected which takes this giant vector to size 4096. So this has size 4096. Then this 4096 goes to again 4096. Right, 4096, and then finally this 4096 goes to, and we know this, right, and in between of course there are ReLUs which we have kind of not written here, and then so I'm taking it up to the top. So you had your 4096, right, after, so you had one giant thing which then came to 4096. From 4096 you went again to 4096, you didn't downsample, right, and then from 4096 the last one, so this one, there is this so-called classifier. So we call this as the classification layer, because from 4096 we are going to our final resolution of 1000, because we have 1000 classes, and then we're going to do cross entropy on it, and you know this very well. But what I'm trying to say is, in real life what you do is, so you have already this model which is trained on ImageNet. As next what you do is you train it on a small data set, right? So you want to train it on a small data set because you only have this small data set with you, and in that case what you have to do is you have to start with so you treat this whole network as a fixed feature extractor, meaning what you do is you just get rid of this, right? You swap the softmax, so you kind of get rid of this, and there's a softmax in the end. Instead of there, you kind of keep it, you put it here, right, after 4096, and then you can fine tune. What you can also do is you can just, so what I'm saying is here on top you remove this bit, right? So you have your 4096 vector, the last one. This is so-called embedding, right? So remember this word, embedding. You can, it is also sometimes called as a latent vector, right? So what does it mean embedding? What does it mean latent vector? You had your, let's say, image, and let's say your image was of high resolution, let's say 100 cross 100. 100 cross 100 is how much? 100 cross 100 is 10,000. Now what we have done is we have reduced this 10,000 to 4096 numbers, right? So we have reduced the dimension. So we have kind of projected this high dimensional image onto this low dimensional vector, in this case 4096. It's not just with images, you can do it also with text. For example, we will see later that there are APIs you can call. You can give it like a chunk of text, let's say a paragraph of text, and it will give you a vector, 1024, a 2048, a 4096 long vector, right? And this vector is essentially a representation, an embedding of your original input, of your original data point onto some other space, and this space we call latent space. And why embedding? Because we are embedding it. This is like an embedding of this high dimensional object onto that low dimensional vector, right? So the only thing I want you to remember is we have some pre-trained model, we put some data into it, right? We put our image, we put our text, we put our speech into it, and out we get a vector. And how do we get this vector? We get this vector by removing the last part of the model, because the last part of the model here, you can think of, this as your 4096 is the output of the second last layer. To this 4096, we multiply a matrix. What size is the matrix? 1000 cross 4096, and this gives us 1000 long vector. So we are just not interested in this, because this is actually the final layer which is classifying it, right? All these rows are learned based on our final classes, our 1000 classes in the ImageNet case. But for us, we may have different number of classes, right? So we don't want the last layer. We just want to throw away the last layer, and whatever we get in the second last layer, we consider it to be a good representation of our data because of that original training on that very large data set, maybe internet scale data set, maybe ImageNet data set. So there are two ways, right? One is where you directly use the embedding and we do something to it. For example, you can do nearest neighbor and so on. But so that is one way to use that embedding. So that embedding is what is valuable. The other way is to fine tune it. What I'm saying is, okay, now instead of, so you had, let's say, your 4096, let's say this is 4096. And now instead of your 1000 classes, you have maybe 600 classes, right? So you have these 600 classes and you want to train only this layer. So this is what I'm saying here. So this is called just swapping the last layer, putting a new layer and only learning this and not changing the weights of any of this. Yeah. The other way is to maybe, so I'll rub this a little bit, right? So, okay. So the other way is where you can also fine tune the whole network, right? So you maybe swapped it in, maybe here you put another layer and then softmax on top of it, and let's say this has 600 classes, right? Now of course you have to train this layer, so the weight corresponding to this layer. What you can also do is you can fine tune the remaining layers, and so for example you can then back propagate through it. Instead of freezing these layers, you can still pass the gradients and update the weights. You can also choose to retrain a bigger portion of your network. You can say, okay, I will throw away the weights that I have in all these and I will, retrain all of the previous part of my network. So this is when you have a medium sized data set. So instead of just, in this case, the fine tuning is not just on this last layer, but it is on, let's say, a bigger part of the network. Yeah, simple. Okay, so now transfer learning, how does it work? You train on ImageNet, and after you have trained it, what do? We go to the next bit where we simply train the last bit. Like I said, we maybe have 600 classes and we train only the last bit and we freeze the rest of it. Or what you can do is you can freeze a smaller part of the model, right? You can maybe freeze just this part of the model and train a bigger part. In PyTorch, you can achieve this by simply loading a pre-trained model. In this case, we load a model called MobileNet, and we will talk about MobileNet and many such models when we talk about the the history and the different models that came out. So here what are we doing? We're just loading this MobileNet and we are then saying, okay, this is my input image size. I should not include my last layer, and this alpha, we'll talk about alpha when we talk about the MobileNet, right? So that's all that there is in fine tuning, right? In transfer learning. So transfer learning is really simple, and that is all that we do when we do transfer learning. One thing to know and remember is that when we do this fine tuning, we always use a much lower learning rate than what was used initially. So for example, if you kind of started with, let's say, 10e minus 4, right, 1 into, so 10 to the power minus 4 as our learning rate. So let's say our lambda was equal to 10 to the power minus 4. What you would do is you would only use, let's say, 1 by 10, right, 1 by 10 of this, which is 10 to the power minus 5, to train, let's say, the last layer. And if you did decide to train the remaining part of it, you would use maybe something even lesser, because you don't want it to change too much, right? So you would maybe use 10 to the power minus 6. Otherwise, I mean, I would invite you to try it, but what happens is you kind of diverge from the original weights, and then you are kind of in a bad place and it's not very useful. So remember, rule of thumb, whenever you fine tune, you fine tune with a much lower learning rate than the original learning rate that was used. So either, an order of magnitude less, so 10 times less, sometimes even 100 times less if you're fine tuning a bigger part of the network. So another thing to remember is there are these cases that can happen, right? So let's say you have very little data, or you actually have quite a lot of data. And what can happen is your current data set is very similar to the data set that original network was trained on, or it is very different from what that original network was trained on. So for example, let's say we are talking about ImageNet, right? So like I said, ImageNet is a collection of 1,000,000 images, and each of these 1,000,000 images come from one of those 1,000 classes. Now your current data set is, let's say, something very, very different. Let's say it's maybe medical images. I mean, medical images is still similar, but let's say it's maybe text, right? So text is very different from the images. And now if you were to train your model, if you were to fine tune your model on such a data set, what do you need to do? If you have very little data, you should, and the data set is very similar. Let's say, you now want to differentiate between images of cats and dogs, and cats and dogs are very similar to what you had, or traffic lights. It is again very similar to your ImageNet data set, because ImageNet is images. This is also these are natural images. So all you need to do is you need to just train that additional layer W, right? You have your 4096 vector, and all I want you to do is you want to train this new weight that you've put for, and what is the size of this weight? It is maybe 2 cross 4096, which then multiplies with your 4096 cross 1. Yeah, and then it gives you a 2 vector, because it was you just want to differentiate between cats and dogs. So that's simple. But now you have quite a lot of data. You can start with this, and then you can try fine tuning a few more layers, right? You can try fine tuning a few more layers. And the intuition here is that the initial layers, the initial features, the initial embeddings of the initial layers that the model learns are more generic. So when you do, say, images, you think of this as maybe they're detecting edges and curves, and maybe those very, very primitive structures of a natural image. And then in the later parts, it becomes more and more specific. So then those edges combine and form corners, and then those corners later combine and form shapes. So corners combine and maybe form rectangles and squares, and these rectangles and squares form and combine and form maybe cars and tables. So the initial layers are more generic, and the later layers are more specific. Now so this was the good case when your data set was very similar, lucky. But now if the data set is very different, then obviously the problem is harder, right? So if you have quite a lot of data, well, go ahead and train a bigger part of your network. But if you have very little data and your data set is very different, then clearly you're in trouble. You can maybe try to use features from different layers, concatenate them. So you have one vector from here, one vector from here, one vector from here. You form one giant vector with this just by concatenating it, and then try to learn maybe weights. But when you are in the regime of a small data set, then we'll talk about, in our live sessions, things that you can do based on real problems that you might be facing. So there is data augmentation, there is synthetic data, there is simulation data, there is physics inspired constraints. There are a lot of things you can do, but for now, yeah, let's see on case by case basis what do we have, and we have to kind of think of some clever strategies when we are in the regime of very little data and at the same time a very different data set. Okay.